Okay, it's time to start. Good morning, everyone. Good evening, everyone. And in Sweden, right? It's my pleasure to introduce today's speaker, Professor Mohammad Reza Hesamzadeh. He is a professor in energy markets at KTH Royal Institute of Technology in Sweden. Professor Hesamzadeh research focuses on the topics regarding the electricity market design and analysis, and he used the optimization as a core methodological tool for his research. So he published so many papers, not only in the IEEE transactions journals and energy policy and energy economics, but also the operations research related journals like the EJOR and EMSOL. Today, we are delighted to have him with us to share his research and insights. Without further ado, please welcome Professor Hesamzadeh.
Okay, good afternoon to people in POSTECH. And also here is the morning, so almost 1 hour till noon. So thank you very much, Professor Doingu, for your kind invitation and all of the excellent works you have done to organize this. I was looking forward for this event to discuss this topic with people in the room. Right. So as I was introduced, I'm Mohammad Reza Hesamzadeh. So currently I'm a professor of energy markets at KTH Royal Institute of Technology. So it's now several years, more than 15 years that I'm working in this area of energy markets and network regulations. So the topic of today talk is about transmission network and transmission network investment in electricity, and also the interesting topic of merchant and regulatory incentives. So we know that right now the power system or electricity network is in need of extra capacity for transmission network. There are a lot of investment on the generation side of the market by new wind power plants, new solar cells, and also a lot of investment quite recently on the demand side. And the most distinguished one is growing rate of demand centers. So these demand centers, especially in Europe, and I'm sure all over the world, they consume a lot of electricity. So a lot of electricity means a lot of generation, and it means that a lot of more investment in electricity transmission network. So in this world that we have, we are in a need of extra capacity, extra transmission capacity. We need to go back and look at the procedures that we have for investment in electricity networks and see if we can make it more efficient or more competitive. So here we want to talk about incentive regulation as compared to normal cost plus regulation, which is used in most of the regulatory offices and most of the governments. So the cost plus regulation is simple and also due to this simplicity is very practical. Technically, it's saying that if your expansion cost is $1 million, so I pay you back A plus a profit margin, 20%, and that is how the current investment policies are studied and approved by regulators. But studies, both in practice and in universities, show that perhaps there are other ways to make the investment in electricity network more efficient. And then researcher started talking about incentive regulation, and some of them are a bit more ambitious, and they are thinking about merchant investment in electricity network. Today, I will talk about both of them, merchant regulatory investment and also pure merchant investment. So what is the merchant regulatory investment? So what is the motivation? Why a new incentive mechanism for transmission is needed. So transmission expansion is one of the key policies that TSOs, transmission network operators, TNSPs are doing every few months. Network by itself has a high fixed cost, and once we invest, that investment, that new lines or new asset is a sunk investment. It can't be removed with low cost. And we also have network externalities. And all of these factors makes expansion planning or investment in electricity network difficult and complex. And also on the other side, beside this complexity of planning of new assets, we have complexity of regulation. Network by itself is a natural monopoly. It means we can't think of two or three network operator competing with each other to build a new line. So it's not efficient. It doesn't work that way. While the type of competition that we have used for generation sector and load sector is more or less we sell out the generation sector to private companies, we sell out the load sector to private companies, and we introduce competition between them. And then out of this competition, hopefully good market results will be achieved. But this type of thinking of introducing competition is not doable for transmission sector. So we can't incentivize efficient investment in transmission network by just this simple competition policy that we are using for generation sector and load sector. So if we can't incentivize efficient investment in transmission network using the policy, using the solution that we have already used and implemented for generation sector and load sector, then how can we incentivize efficient investment? And by efficient investment, I mean an investment which maximizes economic welfare. Like because network is a common resource that is used by all market participants, and it is a resource that it is a public policy decision. I mean, the investment is a public policy decision, and any public policy decision is approved if it can be shown that it is welfare maximizing. So how can I introduce efficient investment in a network, in a monopoly network organization? You know, when we have a monopoly situation, then we are always worried about this monopoly inefficiency. So how can I incentivize efficient investment in a network operator in order to be ensured that the network operator delivers the efficient investment in electricity networks? So one of the so apart from this complexity, we have the complexity of high fixed costs, sunk costs, a lot of uncertainty, and network externality. We have another problem for this network investment, and then that's a classic regulation problems. So you want to regulate a natural monopoly under asymmetric information. So think of the relation between regulator and a TSO, regulator and the network operator, regulator and Transco. Transco has a perfect information about its network, right? It is the owner of the network. It has a whole department of engineers running the system. They have the full information, expertise, and everything. But regulator, who is supposed to regulate investment, who is supposed to check whether the efficient investment is done here or not, it's in asymmetric information position. Means the same level of information, the same level of data and expertise that exists in Transco, it doesn't exist in regulator. So this is a classical regulation problem, which we call it asymmetric information. Some information exists in Transco side, while regulators don't have access to those. And also regulator, since both regulator and Transco are two different organizations, we have problem of limited enforcement or monitoring. So that's why this classical cost plus regulation is almost needs to be updated. So especially in the current years where the industry needs a lot of investment. And then we have another problem. So beside this regulation problem, we have a market design problem. We have a market, and then most of the electricity markets around the world works based on a market operator running a dispatch, calculate price, quantity, and based on the price and quantity, they calculate an amount called congestion rent, and they use, or it was proposed early in the literature, like 20 years ago, that the congestion rent, the money that and the money that it is technically the revenue of Transco, can be used as a way to motivate efficient investment in electricity network. So there are two problems for this. Number one is that congestion rent is not really a good indicator to motivate the efficient investment in electricity network. I will explain it later on why I'm saying this. The second one is congestion rent is calculated by an organization like market operator, and there should be a way to transfer this congestion rent from the market operator to Transco. And this way of transferring congestion rent from the market operator to Transco is through a set of contract. We call it financial transmission right. Our financial transmission right initially are designed such that, or I mean, at least the plan was that we have the FTR such that the summation of this FTR payout is exactly equal to congestion rent. But in reality, this equality doesn't hold. So the summation of FTR payout might not be equal to congestion rent. So even if we accept congestion rent as a part of motivation for incentivizing good investment in electricity network, the FTR payouts are not matching the congestion rent. So that's another problem with market problem. So now, because of the complexity problem of transmission expansion, because of regulatory problem and market design problem, we need to think about a proper incentive mechanism. So what is incentive mechanism? What is a very clear definition of incentive mechanism? In incentive mechanism, we try to align the Transco profit maximization problem with social welfare maximization problem. So we interpret Transco as an independent organization responsible for efficient investment in electricity network. And then this Transco, since it is an independent company, it has a profit function, which will need to be defined. So the profit function is this pi as a function of K. K is the investment capacity that we are looking for. Pi is the profit of this Transco, the company, the organization in charge of investment. And K is the optimum investment when pi is maximized. So in the incentive mechanism, we have two words. Word number one is where profit maximizing Transco maximize its pi function, its profit function. So that would be this one, and it gives us a solution. And then we have the benchmark solution where the best K happens, where the best K means the K, the investment which maximizes welfare. So that's the second one. This is maximizing welfare as a function of K. So in the incentive mechanism, we want to design mechanisms such that the solution of this pi maximization and the solution of this W maximization, and by solution I mean argument, are the same. Means if the company solves this pi maximization problem, it gives me the same K which will be achieved if I solve this welfare maximization problem. In other words, the private incentive of Transco maximizing pi is aligned with the social incentive of the whole industry. So this is in simple term what we are looking for when we talk about incentive mechanism. Right. So if this is what we want, we just look at the literature to see what types of incentive mechanism or incentive regulatory mechanism we have. So we can broadly categorize the economics literature or regulatory economics literature for this topic under these two broad mechanisms. One of them, I can call it sophisticated complex mechanism, which are mainly based on Bayesian approach. And the other category is more simple non-Bayesian mechanism. So of course, sophisticated complex mechanism, they have better proofs to convince the regulator. It's theoretically it's very elegant, but since it theoretically is elegant and complex, it's not very practical. So it's difficult to implement. But simple, and that is this difficulty to implement is exactly the motivation to go towards simple mechanism or non-Bayesian mechanism. So examples of Bayesian mechanisms are Baron and Meyerson and Lafont and Tirol. So I don't go through their papers. It's a very elegant paper on sophisticated Bayesian mechanism. So they propose a mechanism. And then one of the assumptions of Bayesian mechanism, because it is relying on the Bayesian probability, it needs some distribution function. And this distribution function often is not a public knowledge, right? So that's another difficulty of this. But for practical implementation, people often use simple mechanism which use observable outcomes, means we look at the market operator results, price, quantity, dispatch level, and then we set the incentive mechanism based on this observable outcome. So this is one of the strengths of the simple mechanism. And it is enforceable via constraints and formulas. So even if regulator has limited power to enforce a constraint, it's doable because the whole mechanism is simple. And the general idea of the simple mechanism is exactly the general idea of the whole incentive regulation, that I redesign the profit of the transco such that change of profit, delta P, tracks delta W. And that's the objective for any public policy decisions, that I want to design such that individual actions are aligned with the social action. So I try to, I mean, use it using this, explain this idea using this notation, that under simple non-Bayesian mechanism, I want to design regulatory constraint and mechanism such that the change of private company profit is aligned with the change of welfare. So the one that we discuss it here in this talk is HRGV, which is technically categorized under simple implementable mechanism. The two tradition of a simple mechanism. So regulatory mechanism can be categorized as complex and simple. And if I want to further categorize simple mechanism, I can categorize it under A and B. A is subsidy-based mechanism, which goes back to these two papers by Loeb and Maggett in 1979, where profits set equal to welfare by subsidy, and then ISS, incremental surplus subsidy by Sappington and Sibley, where we reward incremental surplus. The strength of the subsidy-based mechanism is that once we implement subsidy-based simple mechanism, you can get the efficient economic welfare solution immediately. So the efficiency will come immediately. But the weakness is that it needs subsidy and tax, and you know that always subsidy and tax create extra discussion around the levels. And there is another category under simple mechanism, which we call it constraint-based mechanism, which goes back to Vogelsang and Finsinger paper in 1979. So technically, what they do, they try to put a cap or a constraint on the price of that natural monopoly organization. So here we don't have subsidy, and then we have only constraint on price of the monopoly. But the difficulty is that it needs a set of iterations. It needs an evolution to get to the welfare optimum solution, as compared to subsidy base, which is getting us the solution immediately. So the HRGV idea, which is the core discussion today, is technically trying to combine the strengths of approach A and B together and propose something of incentive regulation, which is simple, implementable, and also having the strengths of these two approaches, A and B. So we combine the best. So we combine the subsidy-based efficiency without technically introducing subsidy, and also embedding surplus increment in a two-part tariff framework. So can think of HRGB as a convergence of A and B, where the best of these two worlds are combined. I will explain it now what it is. So why I'm saying HRGB is implementable? Because, I mean, in a slide from now, I will explain the equation, and you see that it's a very simple mechanism, which can technically look after the high fixed cost, low marginal cost price signal. So it is defined based on the fixed cost, marginal cost, and price signal. So all of them are observable outcomes. Also, for implementation, we don't need to introduce any new organization. It is a way that we suggest that Transco, transmission company, and market operator or ISO can communicate to each other. And as a result of this, the maximum economic welfare is achieved. And all of this process, the whole HRGV regulatory mechanism, incentive regulatory mechanism, is based on observable data. So we don't need any forecast or prediction, or at least we don't need any forecast or prediction for the base implementation. So that's why it is very fit to electricity network. So in the original HRGV paper, we apply and discuss the HRGV in the context of electricity industry. So technically, by transmission, we mean electricity transmission network. But quite recently, one of my former graduates has started looking at this HRGV mechanism, and he's now working to show that this mechanism is not specific to electricity. So you can, for example, apply it to the gas network or hydrogen network. So although the mechanism in the original paper is explained in the electricity sector, but it doesn't limit it to electricity as a context. Right, so let's see how this HRGV works. So HRGV is simple regulatory incentive mechanism. It works based on a two-part tariffs for transmission. So first, I assume transmission as an independent company with its own profit function. So that's why I'm calling it Transco, transmission company, and it has its own profit. And now in the HRGV, we carefully define the profit of these Transco such that later on we can regulate it to incentivize efficient decisions. So we use two-part tariffs. The first part of tariff, we call it variable part. And that variable part is calculated based on nodal prices or congestion charges, right? Nodal prices are publicly available, so it is observable, so it is nothing special. The second part is a fixed part, which is, I call it F, and this is the F, which technically help us to incentivize efficient investment in transmission sector. So HRGV, think of it as a two-part tariff. Part one is a variable part two is a fixed part. And then by adding these two parts, fixed part and variable part, I calculate the revenue of the Transco, right? So the revenue of the Transco, the money that it collects from the market, composed of a fixed part plus variable part. Variable part is something like this. Pi is nodal price. Q is the quantity which is traded in the industry. So sum of PQ is the variable profit plus a fixed part F, which I'm adding to this variable part. So if I want to write this general revenue formulation for a specific transco in electricity sector, the revenue can be written as a merchandising surplus plus F. So what is merchandising surplus? In electricity market, if you think of transmission network as an organization which buy electricity from load side and sell it to generation side, so under nodal pricing, the money that we charge to the load is higher than the money that we pay to generator. So this difference between what the load pays to the transco and what transco pays to the generator is called merchandising surplus, a surplus which is generated because of transferring power from generator to load. And this merchandising surplus, we take it as a variable part of transco revenue, right? So that's a variable part, and it is calculated from the market quantities, right, and prices, and all of them are public. Plus, this F is a specific to HRGV, so we are adding this F to revenue term, right? What is the problem with this formulation? So if I define the revenue of a transco as MS plus F, right? And perhaps if I'm thinking about investment, I should write it profit equals to MS plus F minus investment cost to write the whole profit formulation. Now, the problem is that when we invest in the line, when the transco invests in the line, as a result of that investment, the merchandising surplus will be reduced, right? So if the transco adds a new line to the system, the level of congestion in the system, which is merchandising surplus, will be reduced. And that's a key theoretical part where defining merchant investment based on MS technically failed. Because if I think of transco as a company with revenue equals to merchandising surplus and the cost equals to investment cost, that transco doesn't have any incentive to invest in the new transmission lines because as soon as it invests in a new line, the congestion rent, which is equal to merchandising surplus, will be reduced, means by new investment, he is losing a part of its revenue. So no transco will do that. And that was exactly the theoretical reason where the merchant investment based on merchandising surplus failed. So there were a set of practical examples in few countries where they rely on this thinking of MS minus investment cost as a merchant investment merchant investment design for investment, but all of those companies technically, they couldn't survive. So eventually they became fully regulated. So the key difference between HRGB and that pure merchant mindset is that we have added this F to the revenue term. Now let's see what does this F do. So key design move, update fixed fee means F by actual customer means generator and load both surplus chain, right? So I'm saying that beside merchandising surplus, I need an extra term F, which I call it fixed fee. And then how do I define fixed fee? Fixed P in regulatory period or planning year T plus one equals to fixed P in the previous one, in the previous year or previous regulatory period, plus change in customer surplus. And by customer of the network, I mean both generation and load. So both of them are customers of the network. So I'm saying that I add a fee and I update this fee using this regulatory constraint. FT plus equals to FT plus change customer surplus. Now, this is the constraint which is enforced by regulator. This is the constraint which is enforced by regulator. Now, let's see if the regulator has enough information to track these constraints and import it. FT is the fixed fee in the previous period. So technically, regulator knows it very well. change of customer surplus is technically change of load surplus plus change of generation surplus, which can be calculated by the market data, because surplus is nothing except profit, and profit for calculating profit you need price and quantity. So this is also we can calculate this part also using the market public data. So this means that this new constraint that we are introducing can be easily implemented using the current information and data we have in the market. So then the profit of Transco will be revenue plus this fixed fee as a part of fixed fee of the Transco as a part of revenue minus investment cost. And the fixed fee is regulated by Transco. So, we can, in a few slides, I show that if we design regulatory constraint and if we design regulatory mechanism as a profit maximizing Transco with pi equals to this revenue minus investment cost, subject to this regulatory constraint, ft plus 1 equals to ft plus change of CS, regulatory period T, then this whole mechanism incentivizes the efficient investment in electricity network. Means the Transco maximizing its pi, and at the same time, by maximizing pi, it also maximizes the economic welfare in the system. In other words, we are aligning private incentives of Transco, maximizing pi, with the social incentive of regulator, maximizing social welfare. So the procedure, the market organization is as explained here. So it works like ISO, or the market operator computes the market prices, quantities, and flows. And then the regulator, out of these public quantities, can compute change in the customer surplus. Using this regulatory constraint, it calculates F or update F, and then it use this F to incentivize Transco to do economic welfare maximizing decision. So using this simple mechanism, we have shown that the Transco decision means if pi maximizing decision of Transco is exactly the welfare maximizing decision. And this is a simple slide of a logic behind it. So see, if I have a social welfare decomposition, welfare of the whole electricity market can be written as load surplus, welfare from the load, welfare from generation, generation surplus, welfare from network, merchandising surplus, minus investment cost. And then if I write pi in our design, it is revenue minus cost. And revenue is MS, merchandising surplus, plus F that we introduced, minus C. Now, if I do delta from both sides of W and pi, delta pi equals to this, and delta W is equals to this. And then look at the definition of F, or delta F is change in load surplus and change in generation surplus. So if you compare this expression of delta pi with this expression of delta W, you just need to define delta F, change in fixed fee, or update F based on the change in the load side of the market, surplus, plus change in the generation surplus. So in simple form, if we update F using this formulation, then we get the economic welfare maximization solution. So HRGV makes the Transco internalize change of customer surplus in cash terms and combine it with merchandising surplus. This money is enough to bear the full cost of investment and also achieving the economic welfare maximizing decision. So using this regulatory mechanism or regulatory constraint, technically incentivize the efficient investment in electricity network. Remember, Transco in our formulation now is a private company, Transco with its own pi. We have regulator, we have the market operator, and the mechanism puts this organization such that the outcome of investment is efficient economic welfare solution. Right. So that's one way of doing efficient investment in electricity network. On the math side, for Operation Research Society, so we try to model the whole mechanism using a single optimization problem. It turned out that this single optimization problem is a bi-level optimization, where in the upper level, you maximize the pi of the transco, which is merchandising surplus plus fixed fee minus investment cost of transco, and then subject to regulatory constraint, which tells regulator how to update fixed fee. Fixed fee in each regulatory period or each planning period equals to fixed fee in the previous one plus change in the customer surplus calculated by the market operator. And then subject to ISO optimization problem. So in the lower level, we have ISO optimization problem where we maximize the total surplus subject to all of the network constraints. So this regulatory mechanism can be solved or can be formulated as this bi-level optimization problem, where we have pi maximization, regulatory constraint on F, and then finally the ISO optimization problem at the lower level. So if we solve this optimization problem for a general case of any network with any number of nodes, you can see that the solution of this bi-level optimization problem is exactly the solution of one level optimization problem where you just maximize W. So this bi-level formulation technically opened a lot of questions for ORP society. Okay, if can I model a storage in this optimization problem? That was a one project that we did, and then can we model more sophisticated electricity market participant in the formulation? That's another question. So what HRGV effectively implements by substituting the fee update into profit, the transco optimization internalized surplus changes that the regulator wants. So I mean, I hope it is clear by now that HRGV is very simple. Technically, what it says is that I make a company responsible for transmission network investment, Transco, and then I define its pie based on a two-part revenue and the investment cost. The first part of revenue comes directly from the ISO, from the market. The second part is defined through a regulatory constraint. So out of this setting, we can prove that the efficient investment in electricity transmission network will be achieved. Right. So welfare equivalent transformation, if I want to do everything in one slide, so core results in one slide. So that's the maximization of the transco, merchandising surplus plus F minus C over different regulatory period T, subject to regulatory constraint update. So why this gives us the economic welfare solution? So see, instead of summation of TFT, because here I have delta FT, right? So I do sum on all T delta FT, and then this means that sum on all T delta consumer surplus T based on this equality. And then if I put instead of if I get FT from, so if I expand this part to sum FT plus F0. F0 means if you have regulatory period from period 1 to 10, the period before 1, the initial period, I call it regulated period 0, which has an F0. So this sum on T delta FT can be written equivalently like this. Now, if I replace the left-hand side of this expression in the objective function here, you get to this optimization problem, which is exactly economic welfare maximization problem. So it means that while the transco on the surface looks like only maximizing merchandising surplus and FT, but behind the scene, it is maximizing economic welfare. So the transco is happy because it achieves the highest profit from the market, But at the same time that the transco is happy, the regulator is also happy because the maximum economic welfare is achieved. So you can interpret this as a mechanism design step. Profit maximization is rewritten, is reformulated to include the welfare relevant surplus component. So that's the core message of HRGV. I rewrite the profit function such that the change in the surplus somehow is reflected in the profit function. Right, a simple two-node example. I think this I took it from the original paper. I think I go through this. I don't explain it. The proof is in the paper for those people who are interested in theoretical work. It's there. You can go through it, but it doesn't have any new story. It just shows that for a two-node example where you have the real generator and load and electricity network, the mechanism works and you get the efficient prices. Right. Now, the second, so far I have explained HRGB, right? So it's a simple regulatory incentive mechanism. We technically incentivize Transco as a monopoly to do the efficient investment in electricity network. So far, so good, very good result. But if you look at the HRGV, you see that still there are some problems with HRGV. One of the problem is that still there is a role of regulator in the HRGV mechanism. That's why HRGV is called, sometimes in the literature, they refer to HRGV as merchant regulatory mechanism. Although it is merchant in the sense that it is maximizes the objective function of pi, but still we have a regulatory constraint. So it means that we are not in a world where no regulation is needed. Still, regulatory constraint is there, and regulator needs to look after that constraint. So that was the motivation for us to think about, although HRGV is one step forward from cost plus regulation to merchant regulatory mechanism, but is there a way that we can remove regulatory concept from the mechanism and then just make it merchant investment, means pure based on the market outcome, right? And this is the best ideal case that I think it's like 20, 30 years, people in electricity market were thinking about merchant transmission investment. Can we do investment in electricity transmission network in a merchant way? So, I mean, because of all these problems that you see on the slide, we were thinking about merchant investment, right? So can we do merchant investment? So the merchant investment tries to answer this question, can similar welfare aligned incentive be achieved under merchant transmission investment where there is no regulation, right? So can we remove regulatory constraint or the regulator role from the HRGV and make it pure merchant investment? Right. So why merchant transmission investment was a dream for electricity market for the last 20, 30 years, right? So they suggested several approaches, but almost all of them failed to produce merchant investment. So let's first look at the generation. Merchant investment in generation sector works very well, right? So in the generation sector, if we have a very big power plant, the power plant relies on the market prices, and based on the market prices, if the price is very high, it invests. If the prices is very low and it's not making sense to invest, it doesn't invest. So the investment in generation sector is already merchant profit driven, market-based investment. But this concept is not in the transmission network. So we can't rely on merchandising surplus to signal transco for efficient investment. The first reason is the one that I just explained, and it was that if the transco invests in the network, the level of congestion decreases. It means that transco invests, and as a result of that investment, it loses some part of its revenue. So there is no incentive then for transco to invest. Why? Because congestion rents or merchandising surpluses vanish when investment is successful. So early designs for merchant investment were relying on this exactly merchandising surplus base or congestion rent based approaches, where they were saying that, okay, we build we make up a new organization, Transco, and then we define the revenue of this Transco purely based on merchandising surplus or congestion rent. And then we ask the Transco that you are a private company and you need to cover all of your costs using this market revenue. So this design technically failed, both in theory, because congestion rent goes down as the investment happens, and also in practice, there were companies that were following this approach, and they eventually became regulated, fully regulated. So the change in the congestion rent does not signal the change in economic welfare. AC network also has this loop situations, right? So we have a mesh AC network, and we have loop flows and externalities. And these loop flows and externalities makes the merchant investment almost more difficult. Right. So I mean, the key message here is that the standard merchandising surplus base or congestion rent based or FTR based mechanism for merchant investment technically failed, and they cannot deliver the socially optimal network. And I mean, for time being, take congestion, merchandising surplus, and FTR as a synonym of each other. So they refer to the same concept, right? So if we technically rely only on merchandising surplus or congestion rent to signal companies, Transco, to do efficient investment, this doesn't work. So we need something more. So there are two mechanisms that I introduce here. One of them is based on defining a benchmark and rewarding the Transco based on that benchmark. And the second one is more sophisticated, and it's based on a concept we call generalized FTR. So let's do one by one. First, for the first approach, merge transmission investment. So the merchant transmission investor chooses a network and bears its risk. Since it is pure merchant, there is no guaranteed regulated revenue. If you think of HRGV, we had a regulated revenue of F, but here the F doesn't exist. So compensation must come from the market-based payments. So general design problem, make the merchant objective coincide with the planner. So here I'm thinking of a planner, somebody as a benchmark who solves this economic welfare maximization problem. So it maximizes expected value of welfare for different networks. And then I'm thinking about this merchant company to maximize pie, right? So it maximizes its expected pie from the market for different network J. Now, in the merchant investment, we want to have this J obtained from this maximization problem and this J obtained from this welfare maximization problem to be the same. The simple approach is the approach is very simple. Before going to approach, I do some assumption. First, all of these results that we have is for long run equilibrium. We assume perfect competition. So we assume that generation sector don't have market power, the same for load sector. Free entry or exit of generation, right? So generator can come in and leave. And then no sunk generation investment, right? So under this assumption, I assume another timeline that the merchant company first do the investment, then generators or generating company, Genco, see the Transco decision of investment. And then based on those Transco decision, the Genco does investment. And the outcome, this long-term outcome, will come to the short-term dispatch and prices are calculated. So, I mean, the sequence of move is first Transco does the investment, then Genco sees Transco investment, react accordingly, and then we have the spot market, where from there we can get the dispatch and pricing. So I mean, nothing special. It's a normal market procedure. So what does the social planner solves? The social planner technically solve this economic welfare maximization problem, where it's nothing except summation of short-term surpluses, like marginal value of the demand, multiplied by demand, and the short-term operation cost for generator, expected value over different scenarios, which is this term, minus generation investment cost. This is a second assumption, and then transmission investment cost. So assume that there is a planner who solves this big optimization problem for the whole network of K with several generators and also the market operator. So out of this, the market prices will be achieved, price, and the merchandising surplus will be calculated. So once this is done, we can calculate the prices and merchandising surplus. I'm following the nodal pricing mechanism as a benchmark, but it doesn't mean that we should stick to the nodal pricing. As far as if you want to use zonal pricing, as far as zonal pricing is a good approximation of nodal pricing, the same equations and results are achieved. So out of this, I calculate merchandising surplus, I calculate pi of generation and load. And then at the end, using all these market quantities, I calculate the expected value of social welfare. So it means that if the social planner solves this optimization problem, the expected social welfare that we expect is this term. It's nothing except summation of expected value of the pi for load and merchandising surplus minus the investment cost, nothing more, which everybody can imagine. But then we realized that the change in the economic welfare, that's the key point of this approach one for merchant investment, that the change in welfare is related to minus change in the value of dispatch, right? So it means that the difference between two scenarios of no investment and with investment in welfare is exactly the change in the objective function value of the ISO. The objective function value of ISO, I call it value of dispatch. And this expression is the key one, that change in the welfare is proportional with change in the expected value of dispatch with a negative sign. Right? So this means that this expression motivates a merchant payment based on a benchmark comparison. So technically, the story is you do investment, you as a Transco do the investment, and I have a benchmark calculation. Based on my benchmark calculation, if you do investment in network J, given the benchmark calculation B, I transfer this money, J given B, to you as a reward. That's the reward, which is what? Which is expected value of dispatch for benchmark case, plus investment for the benchmark case, minus expected value of dispatch for the network that you are thinking. If J is the network that you are thinking whether you should invest or not, right? And think of value of dispatch at optimal dispatch ISO cost function, right? ISO minimizes the cost, so think of it as optimum value of that. So I calculate this transfer function, and then the merchant profit of this Transco is technically this expression. So the profit, the same way that I have explained profit for HRGV, the pi for the Transco for network J, any network, equals to the transfer that I get from the regulator minus investment. That's the investment cost, right? So if the transfer thinks to invest in network J, the network J means a topology and a set of lines had an investment cost of this much. So this whole thing is the investment cost. and it receives this much money as a transfer from the regulator. The pie of this merchant investor, I define it like this, right? That's my definition under mechanism number one, where this transfer will happen. Look at this definition. There is no regulatory constraint. If you compare it with HRGB, I had another constraint on F, but here I don't have that constraint. This is pure merchant without any regulatory intervention. Now, if you do a bit of math by substituting, it's not hard math, it's simple. If you just substitute t from this expression here and then arrange the term, you get something like this. Merchant maximizes pi t, which is equivalent to this term. And then here, if you say maximize minus this, so if I switch the sign of maximization to minimization, I get something like this, which is what? I'm minimizing expected value of dispatch for network J plus the total investment cost. So technically, I'm minimizing the total investment cost. In other words, by this definition of pi for merchant transco maximize this pi, get the optimum J, which maximizes its pi, and at the same time, minimize the total cost in the system. In other words, the private incentives and the social incentives are aligned. Quickly to mechanism 2. Mechanism 2 is a bit more complex than mechanism 1. You can think of mechanism 1 is that I set up a benchmark, which is the best solution, and I'm telling the transco that if you want to do an investment, and as a result of that investment, you create change in welfare, that change in welfare, I give it to you as a reward. So that's why the transco has an incentive to have change in welfare. But in the mechanism 2 is mainly based on this concept of FTR. The first design that you can see in the literature for merchant investment is the authors, the researchers were trying to use the concept of FTR or merchandising surplus as a signal to incentivize transco to do efficient investment. But the problem is that if we just take MS as a revenue of the transco, this is not enough for transco to give us the efficient investment. So what we did in the mechanism number 2, first, we design something called GFTR. So GFTR you can think of GFTR as a generalized version of a standard FTR. In a standard FTR, sum of FTR payout is less than equal to merchandising surplus. In the GFTR, the sum of FTR payout is exactly equals to merchandising surplus. Now, we think of a market with two stages. Stage number 1 is a hedge market. Stage number 2 is a spot market. So we show that if we are dealing with the risk-averse market players, means generators are risk-averse, they hedge their risk using some standard cap contracts. Loads are risk-averse, they are dealing with some floor-type contracts. The network operator is also risk-averse. The revenue is merchandising surplus, and it technically handles the changes in merchandising surplus using GFTRs. Now, if we are thinking of a counterparty for all of these hedge contracts, all of these contracts which manages the risk, that counterparty is exposed to, we can prove, to the total economic welfare. In other words, by selling contracts to generators, loads, and transco, the counterparty, the risk management operator, that is exposed to exactly the total welfare in the system. So this means that if the risk management operator wants to maximize its revenue, it needs to maximize the total welfare in the system. In other words, if I go to the risk management operator saying that I want, by I mean transco, we want to invest a new line, And as a result of investment in this new line, the total welfare in the system is increased by 20%. Since that 20% is technically the revenue of the risk management operator or the profit of the risk management operator, the risk management operator has a very clear incentive to fund this new welfare maximizing solution. So by the interaction between generators, loads, transco, and the risk contract provider, we can, through GFTR contract, we can technically incentivize efficient investment in electricity network. So the two mechanism that is completely removing regulator from the scene is number one is benchmark calculation and rewarding transco based on how far you are or how close you are with this benchmark. And the second one is based on rewarding the transco or think of transco as a risk averse market players with the revenue of a GFDR. It wants to hedge this. And then the hedge market operator is technically exposed to economic welfare. Right. So that was my takeaway. So I'm at the conclusion. I guess I did my conclusion just a few minutes ago. We have two different mechanisms for incentivizing efficient investment in electricity network. One of them is HRGB type thinking, where you use a two-part tariff and still you have a role for regulator through the regulatory constraint. And the second one is a pure merchant investment based on the FTR contracts or more generalized version of that GFTR contract, where we remove the role of regulator completely. I mean, the key takeaway from this is that if we want to do this incentive mechanism, the question is how can I design pi so that the maximizing pi and maximizing welfare are aligned. That's a starting point for this. And both of these mechanisms address these interesting questions. There are points to explore further. Robustness of welfare aligned mechanism. We have, I assume a very perfect, imperfect competition and market power reality. We have these situations. For all of my derivation, I assume everything is convex and I could do the first order condition. The reality is that the investment is lumpy and discrete. Uncertainty, I didn't really go into detail of uncertainty modeling. The real AC power flow equation was not there. And also there are some practical implementation challenges that should be addressed based on the context or based on what we want to implement. This presentation is mainly based on these two papers. So I'm now happy to answer any questions that you have. So thank you very much.
Okay. Before the talk, we can have time to, we can have some couple of questions from the floor, or we have
Yes,
some
thank you.
online participants. Any question?
I have a question.
Yes.
Professor Mohammad, can you hear me?
Yes, clearly. Is it so?
Yeah.
Okay.
That's an issue.
Yes.
Regarding the HRGV, I
Yes.
was curious about that surplus of the consumer surplus CS can be explicitly calculated in that bi-level model, or is that this
Yes.
variable is given constant?
Yes, so it is, think of it as a bi-level optimization, and I know your background. So think of it as a bi-level optimization. So the upper level is Transco, and the lower level is ISO. So ISO solves its optimization problem, and out of this, you calculate price, quantity, and flow. And then customer surplus means generation surplus and load surplus is technically the price times quantity of this, right? So once you have these numbers and once you have the result of the ISO dispatch, then profit of a generator is nothing except electricity price times quantity minus cost, and the net utility of a consumer is its utility minus price times quantity. Of course, here I'm assuming that regulator can estimate cost function and utility function of loads and generators. And since in the setup, I'm assuming that there is a perfect competition, so these can be interpreted from their bid and offer functions. So when there is a perfect competition, we are expecting that what they are submitting is their true marginal cost and marginal utility. So from the bid information, we can calculate technically the utility function and cost function. So that's the whole HRGV setup. So this information that the regulator needs, except the utility and cost, is technically on the market operator website. So there's nothing except price quantity. So those are publicly available.
Well, since we give the Transco as the consumer surplus, then is that possible that any consumers loses their money, or because we give them some surplus money to Transco, then so.
Yes, I mean that's how it works. So the mindset behind HRGV is if Transco does investment, and as a result of that investment, some welfare generated in the system, since that welfare is coming from the Transco decision, so we give it as a reward to the Transco.
I understood that.
Right?
Oh,
So
yeah.
that, I mean, the same reward thinking is applied when I do the benchmark, or we do the benchmark for pure merchant. So we are technically in the very high level, we are telling the Transco that if you do a good action, as a result of that good action, you create extra welfare in the system. We give you that extra welfare as a reward to you. I mean, said that, I have seen quite recently some of researchers, they try to put a scaling factor behind this reward and try to play with this reward. But as far as we incentivize Transco to give us the efficient investment, that's good enough, whether by the true welfare or a scaled down version of welfare.
Any other questions? Yep.
Professor, can you hear me?
Yes, please.
Thank you for your great talk. Actually, I have no background on these research.
Oh, okay. Sorry for that.
Yeah, no, but I thought it was very interesting. And my question is about you wanted to align the maximization of the profit and the social welfare, right?
Yes. That's a key one. Yes,
Yeah.
exactly.
My first question is, how do you evaluate the alignment? And the second question is the alignment important for some and for analytics or
Yes.
some like computational way?
Okay. The first question, how do we check alignment? So, I mean, in theory, we prove that if regulators set the regulatory constraint like the way that we are suggesting, and if the pi is the way that we are suggesting, we should expect this optimum welfare situation, right? So, so that's why, since we have a general proof that the mechanism in general gives us the general economic welfare, so if it is implemented, we are also expecting the same thing. But I agree that in reality, there might be implementable issues regarding implementing the mechanism. That, for example, we see that what is realized after Transco investment is not exactly what we were expecting. And that's exactly what I meant in this future research question, that I was saying that when we want to implement this is so far in theory, so we might face practical implementation challenges. For example, we might might see that the real implementation, the real realized investment is not the benchmark economic welfare maximization. And then we need to investigate why the theory and practice are different. So there might be different many reasons for these implementation challenges. What I can say right now is, in theory, it seems that using this HRGB mechanism, we can achieve the maximum economic welfare. And then regarding the computational issue, if you want to solve the whole mechanism, HRGV mechanism, as a one-shot optimization problem, it is technically a bi-level optimization problem. So any computational issue that you can think of solving a large-scale bi-level optimization problem, you can expect it here as well. And remember, this is bi-level optimization. If I want to give you more math property of this bi-level, the lower level is the ISO optimization problem. I mean, in some market is a linear optimization. In some other market is a mixed integer linear program. In some other market, it is mixed integer complementarity optimization problem, right? So all this complexity you expect happening in the lower level. This constraint, the consumer surplus or customer surplus, it has product of price and quantity. So it has this bilinear term in it. So in terms of profit function, FT is linear. Cost, I mean, you can, with a good approximation, assume that it's a linear, but merchandising surplus, again, it introduces some bilinear term. In the original HRGV paper, we have produced a set of reformulation where some of these bilinear terms can be written equivalently as a set of linear constraint, right? Those might help in terms of addressing the computational issue, but again, it's a bi-level optimization. So there was one of our former student who was working on exactly the computational issue of this bi-level optimization. So she integrated a storage to the model and also derived the bi-level optimization. But then in her case, it was difficult to solve as a one-shot optimization problem, and she used a very carefully designed Bender's decomposition to solve the optimization problem. So yeah, all of those math properties are interesting future questions. It is complex. There are complexity in the bi-level optimization. Yes.
Okay, so I think I have a question. So,
Yes.
yeah, I expect that you may have many opportunities to meet the, practitioners and actual policymakers for the, electricity market regulation. But in this kind of research, you used very stylized model, right?
Exactly.
And
Yes.
that stylized model can provide a very nice insight for the how to design the policy and regulation. But in my experience, many policymakers and practitioners, okay, of course they can agree with this kind of insight, but they usually require more detailed model to
Yes.
implement the policies or regulations. So at that time, how can you resolve that gap between this kind of the stylized model based research and the practitioners' perspective?
Yes, I mean, it's very true. So I fully agree. And that's why I was mainly expecting this question almost from all of you, because this is not the first time I'm presenting this. So that's why I end up the last slide with this practical implementation challenges as an open research question. This is, as you said, this is a stylized theoretical approach. But the point is that when we were implementing this approach, or we were designing this approach, the involved professor in this, all of them were very experienced in this network regulation concept. So we were doing our best to integrate the practical limitations that exist in electricity market nowadays in the design of HRGB. So in terms of what type of public data we have, what is the current existing industrial organization type interaction between different market players, market participants. So in the design part, we were doing our best to at least integrate as much as possible the practical difficulties into the design. And then later on, yeah, we did a lot of several presentations for different network operators collecting their views. So now we are working on some of those implementation challenges. But I mean, at the end, I have seen papers published which are motivating this approach, at least for possible implementation in reality. So I can, if you are interested, I can forward a few quite recent papers which are which are technically suggesting from credible authors, which are suggesting technically implementation of this for electricity networks. So yes, I agree, implementation is always difficult and challenging, but that's also an open question that we are thinking. So this has been implemented, this has been presented in different countries, and we have collected comments. So I think with the presentation in your university, hopefully this motivates a bit of thinking both on extending the theoretical part of this, like for example, this uncertainty and market power. And also if it is interesting, I would be more than happy to discuss it with more details with the local network operator, transmission network operator, to see if we can think of a way to implement or test this on a pilot studies. Yes, I'm open to all of this. So technically, I don't have answer to all of these implementation challenges.
Yeah.
So I should be clear in that.
Okay, so other questions? So I think we are done for the questions.
Yes.
And
Thank you very
it's
much.
time to finish. And thank you for giving us the very nice talk. And please give a big applause.
Thank you very much. Thank you.
Yeah.
So thank you very much, all of you, for attending. I hope you enjoyed. Apologies for those who didn't have the background. I was starting with some terms that I thought people are more familiar, but as you said, it's not that much difficult. So I'll try to explain it in a high level language. Would be happy to answer all of your questions by email. I mean, Professor Dongu knows my email address, or I mean, we can talk through. Yes.
I can
So,
share your email address too.
yeah, so any question on this, anything, that's very highly appreciated. And hopefully this creates a very good platform for future collaboration with Professor Dongwu team and also your university. So thank you guys, and I think have a good time.